Swayam Prabha. Digital India. Educated India.
I welcome you to this course on flow through porous media. The module that we were discussing earlier was mass continuity, where we initially in the introduction section we talked about various characterization or the couple of characterization parameters, that is permeability and porosity, and how we can work with, we can establish some flow equations using these two terms that we discussed, and then we tried to see the continuity as we see in fluid mechanics, how it can be extended to flow through porous media. So, in this case we had talked about Darcy's law, and we had talked about mass continuity in Cartesian cylindrical coordinate system to derive pressure equations and velocity profiles. Beyond this, we have talked about the complex potential, that is we had discussed about this complex potential as F z, which is equal to phi plus I psi, where this is referred as potential function and this is referred as stream function. And we have established F z for different elemental flows, particularly which are of relevance to porous media application. For example, a source or a sink, where we have seen that F z would be equal to m by 2 pi ln z, where, or to be precise, if we want to shift a coordinate, we can write this as z minus z 0, and this m is volumetric flow rate per unit depth perpendicular to this screen, per unit depth perpendicular to the screen. So, this is how we had worked with, and we have found out that this is the complex potential for source and sink. Similarly, for complex potential for unidirectional flow, what we saw was that you have f z is equal to u z. This implies flow in x direction, whereas the source and sink means one point, and then flow is either emanating if it is a source, or if it is a sink, then m will be minus, m will be negative, and in that case these would be simply, sink means flow would be all inward. So, this is something which we discussed, and then more importantly we said that if there are 2 unit flows or 3 unit flows or more than 3 unit flows, if they are happening simultaneously in some place, then we can simply superpose them. That means, we can take f z of one elemental flow and take the f z of another elemental flow, and then sum them up, and whatever the sum potential functions are, sum of these potential functions and sum of the stream functions, these can be used as if this in the superposed flow, this will define, that sum will define what is the potential function, what is the stream function, what is the velocity profile. So, using this, so I take this, I give you an example here. The example is something like this. We are talking about superposition of source and uniform flow, and both of them are at the origin. That means, I have, let us say this is the origin. So, on one hand we have uniform flow u z, on the other hand we have a source. Source means So, if you have a flow in a porous medium, you have this kind of a combination, source and uniform flow. That in that case, how would the streamline and potential line would be, and what would be the velocity profiles in this case. So, a source would be, say, let us say I have an injection well here. So, I am injecting, so all are per unit depth perpendicular to the board. So, perpendicular to the screen. So, that means I am say in a 3-dimensional sense, I have a uniform flow going on, and simultaneously we have a well through which we are putting some we are disposing some water there, and the water is flowing in this direction. So, in this case, what would be how the streamline will look. So, we have done this f z is equal to u z, this is the elemental flow for uniform flow in x direction, and this is m by 2 pi ln z, this is the uniform this is the flow for the elemental flow for source. Okay. So, since q in earlier context we defined the production from the well. So, it is basically m is equivalent to minus of q. To be precise, q per unit length, because at the earlier time we had worked with q as a volumetric flow rate. So, m is q divided by h, maybe the depth of the porous medium. So, that also has to be accounted. So, anyway, this is not that important. M is here is a source which is opposite to production from the well. So, now this is here the source is located at the origin. So, our xy system is taken so that the source is located at the origin. So, there is no correction required here as z minus z 0. So, in this case, if we sum them up, we can see here what is the first of all, this z would be written as this z would be broken down into, as we had done earlier in our earlier lecture, x plus I y. So, x plus I y means it is r cos theta, right. So, we have x plus I y. So, this is r and this is x, this is theta. So, x is r cos theta, y is r sin theta. So, r cos theta plus I r sin theta. So, we had taken r common and we had written it as cos theta plus I sin theta, which by Euler's theorem we have used it as r e to the power I theta. So, we have put these ln z, instead of z we put r e to the power I theta. So, r e to the power I theta when we put, then we see here u z plus m by 2 pi ln. Now, z, this z also we can break it up into r cos theta plus I r sin theta. So, now if we, so these are the two elemental flows, one is for the uniform flow, another is for the source. Now, if we try to add them and take only the real component of it. So, first of all, ln of r e to the power I theta. So, ln of r e to the power I theta will break down into ln of a into b is ln a plus ln b, and ln of e to the power I theta is basically I theta itself. So, ln r plus I theta. Okay. So, that is why when we had written the real component is, so when we have m by 2 pi outside, so then this would be equal to m by 2 pi and this would be equal to m by 2 pi. So, what is the real component arising from the source? That is m by 2 pi ln r. And what is the real component arising from the uniform flow? It is u r cos theta, because this is the imaginary component. So, u r cos theta is the real component. So, that is why you can see potential function phi is defined as u r cos theta, the real component of it, and m by 2 pi ln r, which is the real component of the source. And similarly, since f z is written as phi plus I psi, so the imaginary component will be equated with psi. Basically, this f z is equal to phi plus I psi. So, the real component has to be equated with the real component, imaginary component has to be equated with the imaginary component. So, the real component is phi this phi has to be equal to u r cos theta. This is the real component arising from the uniform flow, and m by 2 pi ln z is this one. So, this is the real component arising from the source. So, that is why the phi is written as u r cos theta plus m by 2 pi ln r. And similarly, in case of the stream function psi, it would be just the imaginary component, and the imaginary component here is in this case u I r sin theta. So, this part is the imaginary component because I have I here, and for this part the imaginary component would be m by 2 pi I theta because I have I here. So, if the I into what we have here phi plus I psi. So, I into u r sin theta, that is what I see here, and m by 2 pi theta, I is outside. Okay. So, m by 2 pi theta. So, this is becoming the stream function and this is becoming the potential function. If we simply equate the real component with the real component, left side to right side, and similarly imaginary component on the left side is equated with the imaginary component of the right side. So, now if this is the potential function and this is the stream function. So, this is, so if I say how the streamlines will look like, you must note here that streamlines will look like the streamlines would be lines along which u r sin theta plus m by 2 pi theta is constant. That is what the information is, but still handling this information is not that straightforward. Let us dwell on this a little bit further. Let us try to find out what is the velocity in this context. Velocity in the sense we can work with Cartesian system or cylindrical system, but they are, I mean, we will be toggling between the two. So, now w z, which is the complex velocity, this is the definition of complex velocity. So, complex velocity is w z, that is equal to df dz, which is equal to u r minus I u theta e to the power minus I theta. Where did we get this? This is the vector identity, we had worked on it earlier. How did we get there? You remember u r, this is the u r, this is u r, and this is u theta, this is u theta, and this is our u, and this was the vertical was the v, right. So, this is u and this is v, this is u r and this is u theta, and what we did at that time is we said this angle is theta. So, u was at that time we had written u was u r cos theta minus u theta has a negative component, negative x direction, it has a component, and since this angle is theta. So, this angle becomes this angle became 90 degree minus theta. So, the cos of 90 degree minus theta, that is sin theta. So, u r cos theta minus u theta sin theta, and similarly v at that time we had written as u r, this time it is 90 degree minus theta. So, v component would be u r, the u r in the vertical component it would be u r cos of 90 degree minus theta, which is u r sin theta, and this time this u theta, the component in the vertical direction for u theta, this would be positive because both u r and u theta both are in positive v direction, that component, and since this angle is theta. So, it would be u theta cos theta. So, this was the identity we had at that time, and then we said that df dz was, or by our original definition, df dz was u minus I v, u minus I v. So, we had written it here, we had written it, let me erase a bit. So, we had written it at that time that this u minus I v was equal to then we had u r cos theta minus u theta sin theta minus I u r sin theta plus u theta cos theta. So, what we did at that time is we had taken all u r terms together. So, it became cos theta minus I sin theta and u theta terms together. So, u theta terms together was, when we took u theta terms together, it would be I u theta into cos theta minus I sin theta. So, what do we have here? Then I plus I u theta cos theta, but we have here minus I u theta cos theta. So, then this should be minus sign. So, if this is a minus sign, so then minus I u theta cos theta and minus minus plus, and again I square is minus. So, then this becomes minus u theta sin theta. So, it makes perfect sense. So, this is a minus sign. This is a minus sign. So, now we had taken, what we did is we had taken cos theta minus I sin theta common, and we have on the other hand u r minus I u theta, and then this cos theta minus I sin theta is written as e to the power minus I theta. So, this was e to the power minus I theta into u r minus I u theta. So, that is exactly what we had written here. df dz is equal to u minus I v is equal to u r minus I u theta into e to the power minus I theta. So, then in this case, if we have df dz, that is equal to df dz is equal to, in this case we have u r minus I u theta e to the power minus I theta, that is one thing. So, this is one thing we have, understood, is that this is one thing we have understood, that w z is u r minus I u theta e to the power minus I theta. This is one thing. Another thing is, if we take just df dz, if we just take df dz of this. So, what is f? F is u z plus m by 2 pi ln z. Derivative of u z would be simply u, and derivative of m by 2 pi ln z would be m by 2 pi, and derivative of ln z with m by 2 pi is constant outside, and derivative of ln z would be 1 by z. So, that is exactly what is written here. df dz is u plus m by 2 pi 1 by z. So, u plus m by 2 pi z, ignore this part, this scratch. So, u plus m by 2 pi z. So, now instead of z, we can write z as x plus I y, and then z is x plus I y, x plus I y is equal to r cos theta plus I r sin theta. So, r within bracket cos theta plus I sin theta, which can be written as r e to the power I theta. So, if it is r e to the power I theta, then you can note here that it is, instead of z, instead of this z, we have written it here as r e to the power I theta. So, u plus m by 2 pi r e to the power I theta. So, now this, so what we did here is we multiplied e to the power I theta to the e to the power I theta to both the terms, and outside we put e to the power minus I theta. So, that they all even out. Okay. So, what we did is we multiplied u with e to the power I theta and m by 2 pi r e to the power I theta. So, e to the power I theta in that case cancelled out, and then e to the power minus I theta remained at the outside. See, you can automatically get this u e to the power I theta into e to the power minus I theta. So, this would be e to the power 0, and which is 1, and then so you have only u left, and m by 2 pi r e to the power minus I theta, that is exactly what you have here. M by 2 pi r e to the power I theta goes to the numerator as e to the power minus I theta. So, this is one and the same thing. Why you are doing this is because then if we write put e to the power minus I theta outside, then we can essentially we are going to equate now this df dz with this df dz. So, when we equate this df dz with this df dz, this e to the power minus I theta term will cancel out. So, then we can write this u r minus I u theta, we can equate it with this term, these. Then we can equate real with real, imaginary with imaginary, and get the idea what is u r and what is the u theta. That is the idea. So, that is why we are doing this exercise. So, now here again e to the power minus I theta we can cancel out, that is not an issue. But this inside what we have u e to the power I theta plus m by 2 pi r, m by 2 pi r is a real component, we understand, but u e to the power I theta has both real and imaginary component. So, that is why we have to now break this e to the power I theta again, this e to the power I theta has to be broken down into cos theta plus I sin theta. So, that I can because I have to compare real with real, imaginary with imaginary. So, for that reason we had written here as the real component was u cos theta. So we have this, the real component here is u cos theta, and u sin theta would be the imaginary component as far as this term is concerned. And this term, as far as this term is concerned, this is all real, there is no imaginary component. So, if we sum up all the real component in this, the real component would be u cos theta plus m by 2 pi r. So, that is exactly what we have written here, that u cos theta plus m by 2 pi r, this is the real component within this, what we have within this bracket. Whereas, imaginary component is only this one, because m by 2 pi r does not have any imaginary component. So, minus this plus I sin theta is the only imaginary component, and that is what we had written here. See, we have multiplied outside, we have u. So, this is u cos theta and this is I u sin theta. So, minus I had written and then minus u sin theta I have written. Okay. So, that this minus and this minus becomes plus. Okay. I have intentionally written it as this minus I, because I have to equate it with real minus imaginary something. So, that is why I put it as minus I within bracket minus u sin theta. Essentially, it is plus I u sin theta, which is arising from this term. So, this is what we have in the bracket, and outside I have e to the power minus I theta. So, now if we go by the, now if we start cancelling, we can straight away cancel e to the power minus I theta with e to the power minus I theta, and we can write here the u r would be the real component here. So, this would be the real component, which is going to be u r, and this is u r minus I u theta, and we are equating u r minus I u theta. So, this is becoming the u theta, right. So, this term becomes u theta. So, I could equate this whole thing. I could, in fact, I can clear up the space a bit. So, what we have written here is u r minus I u theta, which is coming from this here df dz. So, u r minus I u theta, this is equal to on one hand we have u cos theta plus m by 2 pi r and minus I of minus u sin theta. So, this is what we have in this case. Okay, e to the power minus I theta and e to the power minus I theta we have already cancelled. So, if this is so, then we can say that the u r is essentially this quantity. So, this is u r and this is essentially u theta. So, that is what I have written here. this is becoming u r and this is becoming u theta. Now, what does this signify? I have first of all, I have what are these u r and u theta? Once again, if I visit, u r is, so my origin was this, right? My origin was, so this is the origin, this is the origin, okay. So, or from origin we had these as the x axis, these as the y axis. So, now we can write these in this velocity in this direction as u and the velocity in this direction as v. This we could have done, but instead of that we have chosen to write it in terms of u r and u theta. So, at any point let us say I am taking some arbitrary point, let us say I am taking arbitrarily this point. At this point I can have u and v, or I can have u r and u theta, okay, in the r theta system. Okay, so, that is what it is, and what we see here is that u r is this quantity and u theta is this quantity. We want to know here, first of all, intuitively it makes sense that if I have a source, that means flow is emanating out and I am having uniform flow. I mean, intuitively what we see here is that the streamlines that are emanating here, let us say this is emanating here, this is emanating here, this is emanating, this is a radial flow. So, this streamline would be then carried down like this. This streamline would be carried down like this, because I have a uniform flow coming from the left. So, this streamline would be carried down like this. So, you can see here at some point it would be this streamline that is arising from here and this streamline that is arising from here, the velocity here would be 0. I mean, that is where it is heading to, unless, I mean, if we have to satisfy this, the velocity, I am creating almost an envelope like this, I am creating almost an envelope like this. So, this envelope, and at this point I can say that the radial flow that is coming from the right and the uniform flow that is coming from the left, they will, these two streamlines, they will hit each other and the fluid becomes static here. So, this is referred as, this point is referred as stagnation point. I mean, intuitively I can see there would be a stagnation point and an envelope. So, all the radial flow that I am putting in here, that would be enclosed in an envelope because of this uniform flow that is coming from the left. Okay. I would like to inform you that this type of envelope, this has a name to it. Generally, this type of envelope in the context of fluid mechanics is referred as Rankine half body. Rankine half body. So, our aim would be with this u r and u theta, our aim would be to locate this stagnation point, where how far it would be on the left from the origin, this stagnation point, and what would be this envelope, what would be the equation for this envelope. Let us target this. I mean, instead of, these are still in general terms, but let us target this and find out what would be this equation for this envelope. So, still, I mean, I can make use of this to find out if I am in a reservoir, in a subsurface reservoir, if some fluid is being fluid is sequestered and then there is a uniform flow going on, to what extent this would travel in the lateral direction, if we want to know ad infinity, if it continues to travel further on the right. So, these are the information we can extract out of it. So, I am going to close this module, this section now. In the next lecture, what I will do is I will revisit this equation, particularly this envelope and the stagnation point, and try to see what all information we could gather out of this superposition of flow. Thank you, and I'll continue in the next session.